In this video, I'll go over the copy constructor and overloading of the assignment operator. I've written this code to demonstrate the copy constructor. I've defined a class mlist. Everything in mlist is public just to make things easier for accessing data. The mlist has an array of integers, and this array is called L. It has a certain capacity. Let's say capacity is 10, and also it has a size. So size indicates how many elements are in the array, basically, or in the list. Here is the constructor of the mlist. Basically sets size to 0. It has an insert function. Return type is void. It allows you to insert an integer such as x. So you will basically assign x to L at index size and increment size. And then you also have the print method, which basically prints the list. So it's a very simple thing, simple class here. Now let's try this class. So with that class given there, let's write this main function. I have created an object of the type mlist. I'm going to insert 8, 9, 10, and 11 in mlist and then get a print out of it. So what I'm going to have, I can show it to you right here. So there it is. There is mlist. I have placed 8, 9, 10, and 11 in there. I'm going to run this code as well. And then I'm going to actually create another mlist, let's say ml copy, and assign ml to it. So right here, a default constructor is executed. The system, the C++ system, offers every class a default copy constructor, also called shallow copy. It is executed when you create an object and immediately initialize it to another existing object. Line 26. That's when the default copy constructor is executed, and it does the member-wise copy or shallow copy. So ML is copied over to ML copy, and then we take a look at ML copy as well. So when I run this program initially, here is the run of the program. We'll just look at the partial output here. Here is the ML. That's with the insertion of 8, 9, 10, and 11 right there. And this is the line that prints it. Then I create ML copy and assign ML to it. The default constructor is executed here, and I take a look at ML copy, and there's ML copy, exactly the same thing, 8, 9, 10, 11. Then what I decide to do is to go to ML copy and change the element at index 0, set it to 100, and then get the print out of both lists. Notice that ML copy has changed because I set the element at index 0 to 100, but it had no impact on ML, meaning that ML and ML copy are completely separate and they have their own memory allocated to them. They don't share anything. All right, so that's important. The key element in copy constructor. I'll continue and move on to creating another list. Continue to create another list, and this is related to overloading the assignment operator. So create a new list. ML list is a new L. Insert 30, 31, 32, 33, and 34 in this new list. There it is. That's new list. I get a print out of it. See out new L, new list print. There is the print out of it, 30, 31, 32, and so forth. And then I'm going to let ML to be equal to new list. This is when a default assignment operator, which is also a shallow copy, is executed. So default assignment operator is executed here. So new L is basically copied over to ML. And I get a printout of ML as well. So there's the new list. After assigning it to ML, this is the value of ML. Very good. It's copied over. Then I go to ML and change the element at index 0 of ML. Change it to 200. Or it could be any other change. It could be a different change. But I change ML. And then I get a printout of both lists. So ML is changed. The first element is 200. But again, no impact on new L. Right? The other list. That one is still 30, 31, 32, and so forth. And that's desirable. This is what we want. Right? Couple of things that you need to pay attention to here is that when the default copy constructor is executed, line 26, when you create an object and initialize it, and when an assignment operator is executed, the default one, when you assign to an existing object another existing object. That's the assignment operator. And notice that in this particular case, as I created new objects, the content of new object and the content of existing objects, they were separate. They were not sharing anything. Now I'm going to change things a little bit. Instead of a list, instead of an array, I am going to basically change the array in this code to a pointer. Rather than L being an array, I'm going to make L to be an integer pointer. And the constructor of the mList, instead of just setting size to 0, it is going to still set the size to 0. There is the constructor of mList. It is still going to set the size to 0, but it is going to dynamically allocate memory for L. So it is going to dynamically allocate memory for L. L is a pointer, an integer pointer, and now I dynamically allocate 10 integers for L. Nothing else is changed. I go over exactly the same code. Nothing is changed. But now I'll execute and run the code. And notice what happens here. Here is ML, insert 8, 9, 10, 11. Wonderful. Here is the ML copy where I assign ML to it, and then take a look at ML copy. ML copy is the same as well. Very good. But when I change ML copy, the element at index 0, I change it to 100 and I print both lists. Notice that also ML is changed. The element at index 0 is also changed to 100. That means that the two objects share the allocated memory. So they are like this, ML and ML copy, they both share the same location. So if I change ML, I've also changed ML copy. And if I change ML copy, I've also changed ML. That wasn't the case for the arrays. But now that I've used pointer, dynamically allocated memory, now the location is shared between the two. Right? And bring out the output. And that same thing is the case for the assignment operator. there is the assignment operator. If you go through the code, we've created a new list, inserted 30, 31, and so forth on it. There is the new list, right? I assigned new list to ML. There is ML. I changed one element in ML, changed the element at index 0 to 200, but new list, the element at index 0 has also changed, meaning that they're sharing the same location. Therefore, the default copy constructor and the default assignment operator are not sufficient when you have a dynamically allocated data member in your class. You have to supply a new implementation of those two, right? And here is where I supply the new implementation. That's for the copy constructor. I'm going to copy this, Control C it. There's the copy constructor. I'm going to bring it into the code, and right inside the class, I'm going to place it in there, Control V. This is the copy constructor, right? It basically overrides the default copy constructor. This is also called deep copy, right? By deep copy, that means that it actually creates separate memory spaces for the variable so that they don't share memory location. And notice how this is done. It is in fact, when this line in the main, when I created mlist, let's say ml copy is equal to ml. Remember that line in the main? Right here, this line in the main, that's where the copy constructor is executed. When you execute such a line, the following code will be executed, right? There is an implicit object. The implicit object is ml copy, is the left-hand side. And then the right, the parameter, is the object on the right-hand side of the equal sign. So what happens here, you go to this size, that means that the implicit object size is equal to right size. So you're making sure that the size of ml copy is the same as size of ml. And notice that you explicitly go to this L and you allocate memory for this newly created ml copy object. You allocate memory and then copy over one by one, copy over the elements of the list in the right hand side, ml, which is the right. You copy it over to this implicit object. When you do this, so we have this new copy constructor, I'm going to re-execute. Let me also one more time show you. This was the case when we didn't have the copy constructor. I changed ml copy and that change impacted ml because they were sharing memory. I'm going to, with that copy constructor, let me run it one more time. And notice that that is not the case anymore. So I change ml copy, but ml holds on to its original values. But the assignment operator is still, when I change ml, new L is also changed. So we also need to supply a new assignment operator. And here it is. And there's the new assignment operator. Control C. I'm going to bring it in. Control V. This is an overloading the assignment operator, right? And very similar to copy constructor, you have the implicit object on the left-hand side, and you have the object that is passed as a parameter on the right-hand side, right? This is when you executed the line ml equal to new L in the code, in the main code. new L is the right, and ML is the implicit object on the left-hand side. First, you make sure that the objects are not the same. If they're the same, then there's no reason to copy one onto another one. If they're not the same, you set the size of the implicit object to the size of the new object. You delete whatever was allocated for ML, the implicit object. You delete all those object, basically, all the spaces, and then reallocate, delete L, and then reallocate the same number of space as the size of the right list. So you're basically reallocating new space so that new L can fit in the left-hand side, and then copy things over. Make sure that you return star this as well. Now with that in there, I go back to debug and then run the code. And here now, after assigning new L to ML and then changing the value of the first element in ML to 200, notice that that has no impact on new L. New L holds on to the original values. All right, so in summary, if the classes you create don't have any pointers or dynamically allocated memory, you really don't need to supply copy constructor and overloading of the assignment operator. But if they do have pointers and dynamically allocated memory, then you have to supply your own copy constructor and assignment operator. Otherwise, the two objects, in case of dynamically allocated memory for the data member, the objects will be sharing that dynamically allocated memory. So if I use one object to change the value of data, the other object will be impacted and we'll see the change as well. That's not desirable, basically. All right.